Okay, so in this topic, I will talk about the basis and dimensions. Basis and dimensions. The concept of basis is actually, well, you can say that it is the inverse of the concept of span. So, for example, if we have some vectors, okay, so two vectors, say a vector u which is 1 0 0 and vector v which is 0 1 0, okay, 0 1 2 or 0 1 0, but any vector. So we can see that any multiple of these vectors, for example, if we multiply u by some scalar and then multiply v by some scalar and then add them together, then that will be that new vector will be in the span of that vector. So, but if on the opposite side, so for example, if we use a scalar, say k is equal to 2, here we use a scalar l is equal to 3, so then ku plus lv will be a new vector. So that means k2 k with k it will be it will be 2 times 1 2 0 0 and then plus 3, that is 0 3 6, so we will get 2 3 6. Okay, so we will say that this vector 2 3 6 is in the span of this u and v. So conversely, or if we go backwards, if we will say that if we have this vector 2 3 6, so we can say that these vectors u and v are the basis of this vector, this resulting vector ku plus lv. So in the basis, then that means we try to find those component vectors for some given vectors. Okay, so we will try to find the basis. So let's see it with the help of some examples. So suppose we have suppose we have a vector, rather two vectors represented by this. So this is the these are the x and y axis. X and y axis. So for example, one vector is this and the other vector is this. So suppose these coordinates are 2 3 and this coordinate is minus 2 1. Okay, suppose, okay, minus 2 1, so minus 2 1. So in this case we have two vectors u which are represented by 2 3 and v which are represented by minus 2 1. So then can we have the basis of these vectors? So the answer is yes. So for example, if we say this if you take this vector v, so this vector v can be obtained from u. Okay, sorry, cannot be obtained from u, because these are the two independent vectors. These are two. So for example, if we take multiply 2 by minus 1, so we get minus 2, but we cannot get 1 from here by that same scalars. So these u and v are independent vectors. So if these are the independent vectors, So what we can say that these two if these are the two vectors, then they form a basis for all the other vectors in R2. That means all of the other two component vectors. So it means that if these two are independent vectors, and then if we take any third vector, okay, say we can take any third vector W, maybe 1 minus 1. So now it is possible that this W can be represented by some scalar multiplied by U plus some scalar multiplied by V, that we can show with the help of the solution. So in this case, since the U and V are independent, so we can represent it independent, and then we can represent them as some combination to make it a third vector, okay, in R2, or any other vector in R2. So therefore U and V make a basis in R2, okay, in R2. Okay, next we can check for this situation when we have only one vector, not two vectors. So for example, if we have this one vector over here, maybe these coordinates are 2, 3, okay, for example. So if this vector is 2, 3, U is equal to 2, 3. So does this vector U 2, 3 make a basis in R2? So our answer will be no, because for example, if we say take some other vector W, say maybe 1, 0, okay, or any other, maybe W2 is say 3, 5, unless the components of W are not the multiples of these components 2 and 3, we cannot say that this vector U makes a basis of any vector in R2. Okay, so for this it is possible, okay, because we can get it, but for this it is not possible. So if there is a single vector in R2, so then it will not make a basis in R2. So in this case it does not make a basis. In R2. Okay, so our short answer is that one vector cannot make a basis in R2, or therefore our answer is no. Number 3 is if we have 3 matrices. So for example, this 1, 2 and 3. So suppose this matrix is U, this is V, this is W. So U is, maybe we can take U as 2, 3, V as say minus 3, 2. Okay, I mean these numbers does not matter, but just for the illustration purpose, in W as usual, because both are negative, so no, X is positive, so W maybe you can take like 1 minus 3. Okay, so does these 3 vectors are necessarily and can make a basis in R2? Our answer is no, because you can't have 3 vectors as a basis. For the vector to be the basis, we should have in R2, for the vectors to be basis in R2, we should have not more than 2 vectors, because if there will be any third vector in this case, third vector will be necessarily be a linearly dependent on the other two vectors. So for example, if I take this vector, so we can find some solution for this. So for example, we multiply with what's some number with u, and then multiply this this number v, and then we can get the third vector. Since these three vectors are not independent in this case, so they cannot form a basis. These vectors cannot form a basis in R2. So they cannot form a basis in R2. Form a basis in R2. Number four is this. For example, if you have two vectors, so one is this, another is passing through 0 through the origin. So that means one vector is u is equal to say maybe 2, 3, and the other vector is v, which is -2, -3. Okay, both are like opposite vectors. So since these vectors now lie on the same line, hence they are linearly dependent. These two vectors are linearly dependent with each other. So for example, if you multiply this 2, 3 by -1, so we get the other vector. So since those two vectors are linearly dependent, so they cannot form a basis in R2. Okay. So in this case, in these four cases, only the first case can form a basis in R2. So here we have two vectors, both are different. So here we have just one vector, it does not make a basis, and here we have the three vectors. They cannot make a basis because the third vector would be necessarily be dependent on the other vector. Will not be independent of the other two vectors. And then the last one also, for the dependency situation, they cannot form the basis. Okay, now the next question is, if we are given a subspace as this, so for example, span of three vectors, 1, 0, -2, 3, -2, 2, 4, 2, and 3, -1, -6, 5. So if this is the subspace which is given to us, it is a subspace, of course, and then we can check it by the methods previously discussed. It is a subspace. For this subspace, we have to find the basis. That means minimum number of vectors which are needed to define this subspace. So in another word, if we want to find a minimum number of vectors to define the subspace, which means that indirectly we need to convert them into the row echelon form, and those first columns, or maybe the rows, will define those vectors. I will continue this in the next video clip.